Hello, this is Fırat Tigrek. In this screencast, I will explain how the Newton-Raphson and Gauss-Newton methods work. We use them to solve nonlinear estimation problems. Newton-Raphson searches for the parameter that sets the value of a function to zero. Gauss-Newton method is based on the linear approximation of a nonlinear function. We will see how these methods work on a nonlinear estimation problem. Let's first look into the Gauss-Newton method, and let's start with the problem definition. We have a signal model that has an amplitude that grows exponentially with time. So, the signal model is the nth power of theta. We want to estimate this theta from the data samples xn. The least squares estimation is derived starting from the squared error term, which is also written in terms of a vector multiplication. The signal vector S theta is a column vector that consists of the exponential signal terms. The least squares estimation is obtained by finding the value of theta that maximizes the squared error cost function. So far, we are in a familiar domain of least squares estimation. However, the way we derive the least squares estimation calls for writing the signal model in terms of an observation matrix multiplied by the parameter vector theta, a scalar actually for our current problem. And we cannot write the signal model in this linear form. This is a nonlinear least squares estimation problem. So, what shall we do? One way to go is to linearize this signal model. How? Through Taylor expansion. In a nutshell, through Taylor expansion, we can write a function in terms of an infinite sum of its derivatives at a single point. But we are going to use just the first term. So, we are approximating the function at a specific point, theta 0, by its value at that point and its first derivative at that point. How exactly does this translate into an observation matrix times the parameter? Let's see this Taylor expansion in action. The derivative of the nth entry of the signal model yields theta times a constant determined by theta 0 times n. So we can reorganize the signal model into the desired form plus a constant determined by theta 0. We can write the signal model in vector form to reveal how the linearization works. Finally, we have an observation matrix, H. But what did we do exactly? Here is an animation of how the linearization works. On the left figure, we have the actual signal model plotted for different values of the controlling parameter theta. Marked by the black line is the theta 0 value we choose for linearizing the function around. You see on the right the linear approximation to the signal model around the theta 0 value. What happens is, for each time index n, we replace the actual signal model with a line over R that has the same value and the same first derivative as the actual signal model on the point of linearization theta 0. Our goal, we want to calculate the change in the error function when we change the parameter theta. Instead of using the actual function, we use the linear approximation, which behaves very similar to the actual function around theta 0. So, what happens if we calculate the least squares error using this approximation? Note that the approximate function changes with theta 0. So our initial value is important. More importantly, when the estimate theta hat is far from the initial guess, it means the approximate function is also quite different from the actual signal model. A recursive approach is needed. The recursion emerges from the least squares estimation. Let's continue with our approximate signal model and formulate the least squares error for linear signal model. The least squares error function is as follows. Looks complicated, but we can group the data and signal components that do not depend on theta and call it x prime. Now, let's fast forward to the least squares estimation formulation with this x prime. When we put back the x prime in the estimation formulation, we get an interesting result. We have an estimate that depends on our initial guess, theta 0. Moreover, since we know that the linear approximation is not accurate when the estimate of theta is displaced away from theta 0, it makes sense to update our solution once more using the estimate. This defines our recursion. At each step, we calculate an estimate for theta and use that as the point for linearizing the signal model to calculate an estimate once more. We continue this recursion until the difference between two consecutive estimations is below a certain value or a number of iteration steps are taken. Now, instead of linearizing the signal model, we can search for the parameter value that sets the derivative of the cost function with the nonlinear signal model to 0. Let's work this out in the maximum likelihood estimation setting. To formulate the likelihood function, we need the noise distribution. Let's stick to white Gaussian noise for convenience, but the principle is the same for other noise distributions. The likelihood function is formulated as usual, and log likelihood is used to find the maximum likelihood estimate theta hat. To maximize the log likelihood function, we need the first derivative of the log likelihood function and set it to 0. To see how the derivative of the log likelihood function looks like, let's just go from vector notation to sum notation. The derivative operation is commutative over sum operation, so we end up moving the derivative inside the summation and obtain this equation that has to be set to 0. The way to solve this one is actually very similar to what we did with Gauss-Newton method. We will linearize the derivative of the log likelihood function. That means we take the derivative of the log likelihood function and write linear approximation to the derivative of the log likelihood function. The solution to this equation is quite straightforward, independent of the log likelihood function itself. Independent in the sense that independent of its form. Of course, we have to submit the log likelihood function into this equation to find the final answer. The estimate, in the end, is the sum of the initial guess with the ratio of the derivative of the log likelihood function to the second derivative of the log likelihood function. So, what is the Newton-Raphson method doing exactly? On the left, you see the estimate theta hat through the iterations of the Newton-Raphson method. On the right, you observe the Newton-Raphson method in action. We are looking for the point where the derivative of the log likelihood function intersects 0. At our initial guess, we find the linear approximation of the derivative log likelihood function and calculate where it intersects 0. That calculation is rather straightforward, but the result is not quite correct, because the linear approximation deviates from the actual function when the estimate is farther from the initial guess. So, we repeat the calculation with the new estimate. Iteratively, the solution converges to the value of theta where the likelihood function is maximized. Final notes before concluding this screencast. These methods are not silver bullets. They may not converge at all, and they cannot guarantee finding the global minimum or maximum. Initial value for starting the iterations may change where their iteration converge. Please keep these notes in mind when implementing numerical solutions to your estimation problems. If you have any questions, please contact us. Have a nice day.